All right, things seem to have calmed down. So let's begin. So what's the setup? So I'm going to fix for the entire talk an extension E over QP, a finite extension. P will be some fixed prime throughout. I'm going to take G over E, connected reductive group. And for the first 10 minutes, I don't need any more hypotheses, but I may as well just say this now so I don't forget later. So let's just assume that G is a quasi-split. I'll fix also pinning and a non-degenerate. Well, let's say and yeah, a non-trivial. Additive character. From E towards QL bar cross. So yeah. L throughout the whole talk, L not equal to P will be some other fixed prime. My field of coefficients for everything will be QL bar. I have nothing to say integrally. That's very interesting, of course. Okay, so let me start by reviewing the 350-page Farg-Schulze paper in about 8 minutes. So what happens in that paper? Well, the main player in that paper is this great thing we saw already in Ava's talk, the stack Bung G. Of course, this is the stack of G bundles on the Farg-Fontaine curve. And we will be interested in sheaves on this. So sheaves on this a priori are a little bit hard to make sense of. And somehow your guiding thing to keep in mind is that this stack is not very bad. It's somehow glued, excuse me, from pieces which are quite simple. And so you have this Kottwitz set also as an Ava's talk. For each element of this Kottwitz set B of G, you have a stratum, this Bung G P inside Bung G. And the strata basically just looks like the classifying stack of the E points of this twisted inner form of some levy of G. I wrote wiggly equal signs because this is only true up to some sort of unipotent group junk, which won't actually matter for the purposes of this talk. Okay, and so the geometry of this thing is quite well understood, and this is reflected in the sheaf theory. And so with a lot of hard work, you can make sense of some category of L-adic sheaves on here. So I'm just going to abbreviate it like this, but for people who want to see the official notation, this is what I'm going to write for D lease of Bung G coefficients in QL bar. Okay. And the way you should think about this category of sheaves is that it's somehow assembled from sheaves on each of these strata. And the sheaves on these strata are not bad at all. So you can write the string of symbols. You can make sense of D lease Bung G B QL bar. And then it's a theorem. This is canonically equivalent to the derived category of the abelian category of smooth GB of E representations with QL bar coefficients. So that's quite concrete. And then you probably won't be surprised to know that there's some functors in both directions that tell you how to glue sheaves living on one stratum into this whole stack. But there's somehow a surprising number of ways to do this. Let me start here. So if you fix your favorite B, there's a functor this direction, IB lower shriek, which kind of does what you think it does, some kind of extension by 0. This has a right adjoint. IB upper shriek. You also won't be surprised to know that there's some way to take a sheaf on the whole thing and do some kind of star pullback to get a sheaf on one stratum. Yeah, sure. You know this already, though. Okay, so this functor, again, unsurprisingly, has some right adjoint, some IB lower star. And then a little more strangely, there's also quite useful left adjoint, and I'm not sure if there's official notation for this. So let me call this IB lower sharp. Oh, this goes up. Okay. And so this is something we kind of understand well as human beings. This is just smooth representations like we already seen in Tasho's talk and some other talks. And this is something a bit more hallucinatory, but you really should think of it as assembled from these as B varies over B of G. Okay. I also want to just quickly mention that there's natural dualities in both settings. So here you have smooth duality. You also have this more mysterious cohomological duality of Bernstein, and these both have sort of adaptations to this Bung setting. So here, this functor Verdier duality. So this is just internal Hom towards the constant sheaf. And you also have this more mysterious so-called Bernstein-Zolovinsky duality. Okay. Okay, so I need to do something which is going to look a little bit weird at first, and I'll kind of hopefully justify it later. So these naive functors in both directions are actually not great in practice because they somehow aren't compatible with L parameters when B is not basic. And somehow life becomes much simpler if you renormalize them a little bit. And so let me just fix the notation. So for any one of these three flavors of push forward, I'm going to write IB, whatever that symbol is, renormalized. And here you have your favorite complex of smooth representations of G of B. You take whatever the unrenormalized thing is, but then before you apply it, you take A, you twist it by a character. I'll tell you exactly what this is in a second. And then you shift it by minus the pairing of some of the positive roots for G with the Newton co-character of B. Okay, and so this delta B, so this is the modulus character of the dynamic parabolic of the Newton point of B. So a priori, that's some character of the E points of the centralizer of the Newton point. But then GB is an inner form of that centralizer, and so their cocenters are canonically the same. And so you can regard it as a character of GB of E. Okay, and because I'm working over QL bar, I fixed a square root of Q at some point. So the 1/2 is fine. Yeah. Sorry? Well, I didn't construct it. I just said there is a left adjoint, but the formal recipe is that you take those charts MB from Farg-Schulze. So those have a map towards Bung and also a map towards point mod GB of E. And you do star pull back to MB, and then you do this natural push forward in the D-least world towards Bung. But I'm not going to need this formula. Yeah. Okay. My justification for doing this will become clearer later. Okay, so that's one side of the story of this categorical local Langlands business. The other side is much friendlier. On the other side, we just have Barton stacks. Everyone likes those. And so I'm going to use some notation that I prefer over kind of heavy notation. So Hagen-Schulze write Z1 of WE, comma, G hat, and then I guess I would put QL bar modulo G hat. So this is the stack of L-adically continuous L parameters with coefficients in QL bar. I'm just going to write par G for this. Okay. And this comes with a map to an algebraic variety. So I'll write XG spec. Hagen-Schulze will write this, but with a double slash. So this is the course moduli. You should think of this as some kind of course moduli space of semi-simple L parameters. Okay, and on QL bar points, this really is parametrizing things of very concrete nature. So in QL bar points, this is literally parametrizing L parameters, which are Frobenius semi-simple. Yeah, thanks. You're going to have to keep reminding me of that. Frobenius semi-simple and with open kernel. Yes, let me write Q for this map. Oh, yes. Thank you. Strange. Okay. And so if you have a semi-simple L parameter, it gives you a closed point of this. This is just an algebraic variety whose geometry is very well understood. And the fiber over a point attached, say, to some semi-simple L parameter phi will just look like some finite union of gerbs for some non-semi-simple L parameters, which somehow semi-simplify to phi. Okay. And so the geometry of this picture is really quite well understood through the work of Parg-Schulze and Zhu, and then also this very nice paper of Helm, Karinchak, Moss. And in particular, this is a local complete intersection, and you can sort of write down exactly what its smooth locus looks like in terms of concrete information, in terms of the L parameter that you're looking at, and somehow you can really get your hands on this side of things. Okay. So these two things look super unrelated at first. So let me just skip from this to one of the hardest theorems in Parg-Schulze, which is somehow the hint that there should be this categorical local Langlands equivalence. So what is this theorem? This theorem is that there is a natural tensor action of the category of perfect complexes on this stack of parameters on this category of L-adic sheaves on Bung G. Which somehow extends and comes from, in a universal way, the action of Hecke operators. Okay, so let me briefly remind you a little bit about what's happening here. So one of the main points in this paper is to construct, using some version of geometric Satake, a Hecke action on sheaves on Bung G. So if you have a representation of G hat, you can say V, you can produce from it an endofunctor TV of sheaves on Bung G. And these endofunctors are really the heart of the theory. They somehow capture the cohomology of local Schmorrer varieties in a very tight way. And using the totality of all this data, you can run Vincent Laforgue's excursion operators sort of machine and produce this construction that they built to somehow go from an irreducible representation to an L parameter in a completely canonical way. But you don't need this to do that. This is something that lies somehow even deeper. And what do I mean when I say it extends the action of Hecke operators? Well, this is some fine moduli stack of L parameters. And so there's a framed thing that lives over it, which is a G hat torsor. And therefore, this thing sits above BG hat in a canonical way. And so if you have a representation of G hat, it gives you a tautological vector bundle on this stack. And the action of that vector bundle in this package is just the Hecke operator attached to V. Okay. So this is usually called the spectral action. Okay. And then the conjecture. Taken? Well, Hecke operators, representations of G hat give you certain objects here, certain vector bundles. And I'm just claiming that if you take one of those objects and then you act by whatever this action is, you'll just get back one of these Hecke operators. So this somehow packages together all the Hecke operators, and it's really using the Hecke action in some functorial way. Okay. And so then they also go further and make the following conjecture, which is that so there is a natural equivalence of categories Yes, thank you. From coherent sheaves, let's say, just to be careful, let me put QC here. So coherent sheaves of quasi-compact support on the stack of L parameters towards like a subcategory of compact objects in this category of sheaves on Bung G. Whose restriction to the subcategory of compactly supported perfect complexes here is given by taking such a perfect complex and sending it to what you get by acting spectrally on a very specific sheaf in Bung G. Namely, the sheaf that you get by taking the compact induction from the E points of my fixed Borel. Remember, I choose a pinion at the very beginning, with all of E of this non-degenerate character, which extends to a character of the Borel exactly because, oh, sorry, this should be unipotent radical of the Borel. See? So this is the so-called Whittaker representation attached to this data. And this should be how you get from something here to something here. So this is completely canonical. I mean, this spectral action is completely canonical. And then you postulate that it should really extend to an equivalence of categories like this. Okay, so this is some. Say again? Okay. Well, maybe we can talk. My understanding is that it's right. It's right. It's actually it's right adjoint. It's right adjoint is the correct object. This functor of extended Whittaker coefficient, but I don't want to talk about that today. Yeah. Yeah. No, there's no choices, but let's just stick with this for today. So this is some kind of categorical local Langlands conjecture. But this is just a name. So, question I'm going to talk about just kind of presents itself. If you stare at this for 1/4 of a second, is what does this have to do with actual local Langlands? Yes. In theory, the country I live in is much hotter than Germany, but in practice, Germany is hotter because there everything is air conditioned. So the answer to this question is that it's complicated. But if you stare at things, you'll realize that for most L parameters in some precise sense, a pretty clear picture emerges. And so this is something I want to formulate as a precise conjecture today. But let me start with kind of the most optimistic guess for what might happen, which is not true. But it's still a useful guiding principle to start with this. So the most optimistic guess is that this equivalence is T exact for some T structures on both sides. Okay, and so if this were true and you had a handle on these T structures, this would let you go from here to some bijection between irreducible objects on both sides. Okay, and you might also hallucinate further that the irreducible objects on Bung G side should be something like pairs B and pi, where B is in B of G, and pi is a smooth irrep of GB of E. And you might also hope that the irreducible objects on the L parameter side look something like pairs. Well, just familial names, as in Tasha's talk. So pairs, we have an L parameter phi, and then a row. So phi, say a Frobenius semi-simple parameter, and then rho, an irreducible algebraic representation of the most basic of these auxiliary groups you can build from phi, just this group S phi, centralizer in G hat. Okay. No, but hallucinations are very useful, right? Because then you wake up and you can try to figure out what's some true approximation to them. Okay. And in fact, this is true on most L parameters. So in a moment, I'll define some specific class of L parameters where I really do think this is true. And the starting point for what I want to talk about is the fact that while this full hallucination is not true, what actually is true is that there should be a canonical bijection between pairs like this, independently of trying to view it categorically. So starting point for today. So a bijection between such pairs B pi and phi rho should exist canonically and depending only on the choice of Whittaker datum. Okay, so my next goal is to make this precise. This is not something that I worked out. This is a precise theorem of Alexander Bertolini and Masao Oe. So let me state this carefully. And then with this theorem, again, we'll try to cook up some sheaves and match them. Okay, so let me recall the following formulation of some version of local Langlands. I should pause and mention that we had some amusing discussion about Platonism yesterday, and I'm an extreme mathematical Platonist when it comes to the local Langlands correspondence. There's obviously some canonical local Langlands correspondence floating out there. It's our job to figure out how to pin it down, but it's definitely there. And this is one way to conjure it into reality. And so this is the so-called BG basic incarnation of local Langlands. And of all the different variants, this is somehow the one that I find easiest to remember. I think this should be attributed to Kaletha and Kotwitz. Okay, and so this says the following. Given phi, we expect a natural bijection between the following things. So on the one side, you have the union over all B in BG basic of the L packet for phi attached not to G, but to this inner form GB of E. And then this should map bijectively towards the irreducible representations, not of this group S phi, but of what people call S phi natural. So here S phi natural is the quotient of S phi by the neutral component of the derived group of G hat intersected with S phi. And this bijection should satisfy some compatibility, where on the left-hand side, you're of course free to forget the element of the packet and just remember B. This, on the other hand, by a classic theorem of Kottwitz, is in canonical bijection with the set of characters of the Galois invariants in the center of the dual torus, or the center of the dual group. And there's an obvious map of groups from here to here, and so you can restrict along that map. And there should be a diagram like this, again, which depends only on choice of Whittaker datum. Okay. Yeah. Please. Okay. No, I mean, I learned it from a paper of yours, so. Okay. Okay, I don't know. Okay. And I should also say out loud, at least, that this is known for many groups. So for GLN, for GSP4, for odd special orthogonal groups, and other closely related groups, this really can be proved unconditionally nowadays. But I don't have S phi appearing. I have this weird S phi natural. I don't have all of BG appearing. I just have this BG basic. And so if you want to get the full geometry of Bung into the picture, this is kind of visibly not sufficient. But it turns out that if you know this, not just for G, but for all its standard Levy subgroups, and you're really clever, you can prove the following theorem. So if you assume that the BG, well, yeah, G, okay, BG basic local Langlands, not just for G, our fixed group, but for all of its standard Levy subgroups. Then you can construct from this a natural bijection. From, on the one hand, the union over all B in B of G of a symbol, which I didn't actually define yet. I'll come back to this in a second. Towards the set of all algebraic representations of this component group S phi, full stop. No S phi overline or flat or natural or hat or twiddle or any extra decorations. And the price you pay is that if B is not basic, this is not an L packet. It's a union of L packets. So this is the fiber of the. Okay, I'll push it up in just a second. Right. So the point is that if B is not basic, well, you always have a canonical L embedding of the L group of GB into LG, but there can be multiple L parameters for GB that become isomorphic after you compose further with this inclusion into the L group of G. And so the fiber of this map will be some union of L packets. Okay. And if you just stare at this for a moment and you vary phi arbitrarily, you'll see that we've actually proved a form of this bijection, or that this is literally the bijection that I claimed is true. So let me say thus varying phi. You get a canonical bijection between exactly these kinds of pairs that I was interested in. On the one hand, you have a B and a pi, and on the other hand, phi in a row. And just so that I can refer to this easily, I'm going to call this the BMO bijection. I should also say this construction of theirs is really clever. It's not a matter of just, staring at this for 10 seconds and seeing that it's easy. It involves doing a bunch of stuff with rep theory of disconnected reductive groups. And in the end, you make 5 choices and then have to check that at every step, one of these 5 choices mattered. So it's really quite cool. It will be justified post hoc by the conjecture I'm about to formulate. But I mean, it's reasonably natural on its own, I would say. Okay, so what you might hope at this point is that with this bijection in hand, maybe on the left-hand side, you can cook up in some easy way a sheaf on Bung, on the right-hand side in some easy way a sheaf on this stack of parameters, and then maybe they match under this categorical equivalence. Now, for some L parameters, this is problematic. And so I want to start by now looking at the simplest possible situation where it's really can be made precise in a concrete, very concrete way. And so definition, which is maybe tentative, but let me just stick with this for this talk. So a semi-simple L parameter phi, I will call it generous. If when we look at it's the pre-image of the closed point that it defines in this coarse moduli space. So a priori, this could be a union of gerbs attached to some huge collection of different non-semi-simple things. Let's semi-simplify to it. And I want to postulate that actually nothing interesting happens. So there's no way to semi-simplify phi. Okay, the pre-image is just one orbit of stuff above it in the stack of L parameters. Okay. Are you asking for yourself or for? Sorry. Yeah. So it's an L-radically continuous L parameter, right? So what I mean is that it's for being semi-simple and it has an open kernel, and that it's, I guess, totally reducible, totally G-reducible. Yeah. It's the strongest possible meaning. Yeah. Okay. And the name is meant to indicate that these are somehow generic, but that word is really overloaded, and they're also nice to you. Yeah, that's why I said this definition is tentative. For some things, maybe you want to impose that this is really true as a fiber product of derived Artin stacks, but I'm pretty sure the conjecture I'm going to formulate is still true without that. So let me give an example right away. So if G is GL2, phi is generous, if and only if phi doesn't look like 2 copies of the same character, or a character and then the same character but multiplied by the usual norm function. Yeah. Sorry? Oh yeah, Q. Yeah, great question. So Q is this map from this fine moduli stack of all L parameters towards its coarse moduli space. Yeah, so the QL bar points of this are exactly in one-to-one bijection with isomorphism classes of semi-simple L parameters. And I'm singling out exactly the semi-simple L parameters where when you take the pre-image, nothing interesting happens. You just have that thing sitting there with its inertia substack and nothing else. Okay. So these are pretty well behaved. So some little facts about these. This proposition. So if phi is generous, then the centralizer group can't be too complicated. So in fact, the neutral component is a torus. And also, just by the very definition, you see that there's some canonical closed immersion from this this gerb into the entire stack of L parameters. And in fact, the whole stack is smooth at this point, and this map is a regular immersion. So then, how do I say this? Let me call this map I phi. So this is the canonical map coming from the definition. So this is a regular immersion, and the stack of parameters is smooth in a neighborhood of it. Okay. Any questions on the setup before I start formulating some conjectures? What? Yeah, probably, but yeah, I already have my hands full with this version though, so. Yeah. Yes, yes. Well, any discrete parameter, a discrete parameter is generous exactly when it's supercuspidal. So, yeah, I should say in Schultz that they formulated some precise guess for how this categorical equivalence or the spectral action, whatever you want to say, how it captures local Langlands for supercuspidal parameters. And so what I want to formulate is natural generalization from supercuspidal parameters to this more general class of generous parameters. No, because their parameters will be discrete, non-supercuspidal. And I don't know what's going on there. Okay, so let's make some conjectures. So first, conjecture one, so let phi be a generous L parameter. So this is somehow the master conjecture in this setting. So then you can do the following thing. Oh, let me that. And suppose I also pick some pair B pi, which matches a pair where I have my specific phi, and then I pick a row. And suppose these match under this BMO bijection. Okay. So then you can do the following thing. Because this I phi is a regular immersion, you can take rho, which is an irreducible representation of S phi, regarded as a vector bundle on BS phi, and push it forward to the whole stack of L parameters. Because it's a regular immersion, this is still a perfect complex, so this is quite reasonable. And now you can act spectrally on the streak extension of the Whittaker representation. And you can ask, what do you get? And the conjecture is that you get exactly the renormalized Schrieg push forward from the stratum labeled by B of pi. We'll stop. Okay, so that's conjecture one. I'm going to formulate two more conjectures and then discuss some partial results and other evidence for these. And then hopefully if there's time, I'll talk about the trivial L parameter, which is very different. So conjecture two answers a question you may have asked yourself, which is, well, I discussed three different ways of pushing a sheaf forward from a stratum to all of Bung. Why did I use this specific one here? And so what is this conjecture? So suppose that I have B pi, which is in bijection with some pair phi rho with phi generous and rho completely arbitrary. Then all three flavors of push forward are the same. I only have 15 minutes, is that correct? Okay. So the third conjecture, the following. So if, again, fixed sum phi with phi generous. So then you can cook up the following object. So I'm going to take the direct sum over all b and b at g. And then for each b, I'm going to take the direct sum over pi in this sort of multi-packet attached to GB and this parameter phi. And then here, I'm going to write down the sheaf on Bung that you get by taking this renormalized extension by 0 of pi. And then this bijection produces from b and pi. Oh, I erased the bijection. But from b and pi, you get this irrep row. And it makes sense to take the direct sum of dim I psi b pi, many copies of this thing. And the conjecture is that this is a Hecke eigensheaf. Eigenvalue phi. Oh, maybe I should also say perverse. Okay. We'll make a series of remarks. So first of all, conjecture 1 plus the expected compatibility of classical local Langlands with duality actually implies conjecture 2. And in turn, conjecture 1 together with conjecture 2 implies conjecture 3, more or less formally. I psi, yeah, I hope I defined this. So it's the representation of S phi attached to the pair B pi under this BMO bijection. It's the first name. But B pi is written in Sanskrit and phi rho is written in German or something, so you have to do some translation between names. Okay. What else do I want to remark? Yeah, so this conjecture 1 also tells you how to compute Hecke operators. Say you have your favorite Hecke operator TV and you want to compute what does it do to something like this? And the answer is just something combinatorial. You write down what's happening on the other side and then use the compatibility of Hecke operators with the spectral action. And so all you have to do is decompose V restricted to S phi tensored with rho into a bunch of rho primes with some multiplicities, and then you'll get the direct sum of the associated sort of atomic things with the right multiplicities. And if you stare at things for a minute, you'll realize that as a special case of this, conjecture 1 implies the Kottwitz conjecture. And somehow for supercrustable parameters, conjecture 1 is more or less equivalent to the strongest form of the Kottwitz conjecture. Okay. It implies everything except the perversity. And then conjecture 2 implies the perversity. But right, I mean, if you believe in this compatibility of classical local Langlands with duality, then this conjecture 1 really controls everything. Yeah. Yeah, good question. So there is a perverse T structure on Bung G, and it's kind of exactly what you want it to be. So the star restriction to Bung GB, you're in perverse degrees less than or equal to 0, if and only if the star restriction to Bung GB is in degrees less than or equal to, well, minus the dimension, which turns out to be this pairing of 2 rho with the Newton cocharacter. Yeah. So those are perverse right T exact, and then IB lower star. Yeah, this is one reason we have to do these renormalized gadgets. So those are perverse semi-exact in the appropriate directions. Yeah. Yeah, this renormalized lower shriek is perverse right T exact, and this lower star is perverse left T exact. And then the sharp thing is a mystery. Okay. So there's a precise conjecture. Again, I want to attribute it to Tasho, and he might object that if you local Langlands should satisfy a compatibility with smooth duality, where if you have, let's say, B pi matches rho phi, right, for a fixed Whittaker datum, then B, comma the smooth dual of pi should match under the bijection attached to the dual Whittaker datum, the pair phi dual in the appropriate sense, comma rho dual. We have to be a little careful about what this means. Yeah. Rho dual, some of S phi and S phi dual are canonically the same, but then to get from rho to rho dual, you compose with the Chevrolet involution. Yeah. Yeah. Sure. Okay. I guess I have like 11 minutes, 10 minutes. So let me say a little bit about what's known. So why should these conjectures be reasonable? So the first case to look at is this case where phi is supercuspidal. Because in this case, things simplify a lot. So in particular, the S phi is just S phi natural. All the stuff in BG that's not basic doesn't contribute. Okay. In this case, this conjecture 3 was more or less proposed by Farg in his sort of original talk, where he introduced this whole vision that he had for how geometric Langlands should really tell you what to do in terms of building local Langlands. And then this conjecture 1 in this case is basically written down almost word for word in Farg-Schulze. Okay. But what is actually known in this case, actually quite a bit is known for various groups. So say all 3 conjectures. Okay. For GLN and unramified unitary groups of odd dimension over QP, and then conjecture 3 is also okay for GSP4, and maybe even add some other groups to these lists. But I'm doing a lot of hard work here. This really amounts to the fact that the Kollwitz conjecture is known in its strongest form for all of these groups, and then you can somehow reformulate it as this conjecture, if you like. Right. And yeah, I apologize for not writing attributions because I'm running a little short on time. GL2, I think this is not true because the trivial L parameter is not generous, but it does correspond to an irreducible parabolic induction. Yeah, so for GLN, a generous parameter, the pi attached to a generous parameter will be an irreducible induction from a supercuspidal, but not conversely. Yeah. Okay, so the problem with the trivial L parameter is that there's a lot of Frobenius non-semi-simple junk in the fiber of this map Q. And I was hoping to say something about this, but I don't know if I'll have time. Yeah. Because in, 2, yeah, sorry. 2. Yeah, 2 and 3 are fine. 1 is, it's known in the non-endoscopic case, and then in the endoscopic case, there's this issue of the possible reordering of the L packets. Okay, so the main evidence beyond the case where phi is supracuspidal comes from this really great work of my student Linus, or ex-student, I should say. And so let me say very vaguely what he did, and then if you want to know precisely, you can ask him, or maybe he can give a talk in the trimester seminar or something. So assume G quasi-split, maybe unramified. And that phi is toral. So it factors through the L group of a maximal torus. Maximal split torus of G. And for technical reasons, you also need to assume that it's L integral. Let me put this in parentheses because it's annoying. And it should disappear once some of the machinery improves. That's L integral, and it's now still generous mod L in some sense. So then conjectures 2 and 3 are true. Okay. And it's also, in fact, true that I only check this for GLN. So if G is GLN, and you keep these same assumptions, then you can actually use all the hard work that Linus did with some slight further idea to deduce conjecture 1. This sort of master conjecture. Probably some other groups can be handled also. Okay, so this is somehow the opposite end of what can happen qualitatively from the supracuspidal case, right? Phi is as irreducible as possible. Sorry, as reducible as possible. Okay. And so somehow together, this is convincing evidence for me that this is the right picture. I guess I have 3 minutes. I really wanted to say something about trivial L parameter. Okay. Okay. Okay, so why were things so nice here? They're so nice because somehow the fiber of this map Q is just this extremely simple thing, this BS phi, and the representation theory or the theory of sheaves on this thing is completely semi-simple. So somehow the atomic things there can't speak to each other in any way, and accordingly, everything on Bung G will somehow decompose in a parallel way. But then if you're curious, you can try to go beyond this case. And so I want to end by talking briefly about an extreme case where things are something much stranger. So now let me assume G is split for simplicity. And phi is the trivial L parameter. So really it's the map that sends everything in the V group to 1 in the L group. Okay. So what happens here? So what is S phi? Well, it's pretty easy to centralize the identity in a group. S phi is just the entire dual group, right? And so you know how to parameterize irreducible representations of this. This is just dominant weights for this dual torus, or of course, canonically, also dominant co-weights for the torus in G. So let me write lambda for some generic element here. Okay. And so this BMO bijection tells you that you should be able to go from a lambda to some pair where you have a B and a pi. You can say exactly what it does. It's extremely easy to write down. So lambda, so tree of comma lambda corresponds to the following extremely concrete thing. And what is B pi? It's literally just the class in B of G of lambda viewed as a co-character for T, evaluated on a uniformizer of E. Okay. What is GB lambda? It is just the centralizer of lambda, so it's a levy in G. And then what is this? It's just the normalized parabolic induction from any rel in GB lambda of the trivial representation. Okay. And in particular, it's an irreducible, tempered, whatever parabolic induction. It's extremely nice from the point of view of representation theory. But what's happening on the other side? Well, what does the fiber of this map Q look like over the trivial semi-simple L parameter? It's all not necessarily semi-simple L parameters whose semi-simplification is the trivial thing. How do you write such a thing down? You send Frobenius to any unipotent thing whatsoever in your group, modulo conjugation, right? And so when you unpack this, what you're getting is that this is just the entire nilpotent cone in the Lie algebra of G hat, modulo G hat in the stacky sense. Okay. And there's an extremely well-developed theory of coherent sheaves on this stack. And let me tell you how to make some of them. So it's actually closely related to things that came up in Charlotte's talk. So over this nilpotent cone, you have this so-called Springer resolution. People usually write it as n tilde. I'm still quotienting by G hat. And you can think of this more concretely. Well, what is the Springer resolution? It's the push out somehow of the unipotent radical of the Lie algebra of the dual Borel along G hat into G hat, but then we quotient by the G hat action. And so if you like, just by canceling things out, this is somehow canonically U hat modulo G hat. Let me call this pi. And yet another way to think about this is as the cotangent bundle of the flag variety for the dual group. And so from that point of view, it has a canonical map eta towards the flag variety. Okay. And then on here, well, sorry. Yeah. Okay. Sorry, but yes. Okay. I'm being a little bit sloppy, but on the flag variety attached in lambda, you have the usual equivariant line bundle, L lambda. And so something you can do, which people have done, is you can take L lambda, you can pull it back from the flag variety towards this Springer resolution. And then you can push it forward along this map pi to get some coherent complex in the nilpotent cone modulo this dual group. And so these are so-called Anderson-Janssen sheaves. And these have been intensely studied by various people in geometric representation theory. And I don't have much time, so let me not say how amazing these things are. Let me just end with one more conjecture. And so the conjecture is the following. So let me say one more thing, which is that by the very way that we constructed this, we have some canonical closed immersion from this towards the entire stack of L parameters. And so the conjecture I want to end with is, what do you have to do to cook this up using the spectral action? So this should be something acting on this Whittaker sheaf. So what goes here? It turns out what should go here is exactly the push forward along this closed immersion of this Anderson-Janssen sheaf, A lambda. But now we're in a situation where it turns out that the different push forwards will not all agree, exactly because the geometry on the coherent side is much more complicated. Somehow, coherent sheaves won't decompose in some completely uninteresting way over the representations of S phi. They'll really sort of talk to each other. And so this will actually be a genuinely different object than the Schrieg push forward. And it turns out that what this should correspond to on the other side is also quite concrete. It's almost exactly the same, except here you twist lambda by the long Weyl element. And it turns out that part of this theory of Anderson-Janssen sheaves is that there's a canonical map in this direction. And there's actually a canonical map from this functor towards this functor in full generality. And those two maps should match. Okay. And let me end by saying that I didn't pull this out of nowhere. So this follows, actually, let me word this even more strongly. This is forced on you by the expected compatibility of this categorical local Langlands correspondence with duality and Eisenstein series. So if you somehow believe not only that this conjectural equivalence is true, but that it satisfies various properties, which again are just kind of copied naively from usual geometric Langlands, and you stare at what's going on, you end up seeing that this has to be what's happening. Okay, so I think I went slightly over, so I apologize, and thank you very much for listening.